Hi, everybody, and welcome to 5-1 probability distributions. So let's first talk about what are our key concepts. So the first thing we're going to do in this section, we're going to introduce the concept of a random variable and the concept of probability distribution. Then we're going to illustrate how a probability histogram is a graph that visually depicts a probability distribution. So we did go over histograms. Hopefully you remember chapter 2, I believe, right at the very beginning. We show how to find the important parameters of mean, standard deviation, and variance for a probability distribution. And then, most importantly, we describe how to determine whether an outcome is significantly high or significantly low. Okay, so that's basically what we're going to go over right now. So let's talk about the basic concepts. So we have what is a random variable? So a random variable is a variable typically represented by X. Doesn't have to be, it just usually is. That has a single numeric value. So here's the important things here. It's numeric, well, single numeric value, and it's by chance for each outcome. And then the probability distribution is a description that gives the probability for each value of a random variable. And we can express it as a table, which we've seen, right? Formulas, which we've seen and not really used much of, or a graph. Okay, we've seen some graphs also. So we're going to just go through and I'm going to show you how everything is done. Let's talk about the difference between discrete and continuous. These are the important words here. And let's say, for example, I have a discrete random variable. Okay, what does discrete mean? It means that I can actually count them. So, for example, if I was counting chairs, I could say, I have 1 chair, I have 2 chairs, I have 3 chairs, and I can count as many as I have. I mean, obviously, maybe I wouldn't get to infinity, but I can keep counting as long as I have chairs, okay? And each chair is 1 away from the next. So it is discrete because each value is separate from the others. So for example, if I were to graph, let's see. Okay, how about this? Let's say I have a box, and in this box, I have 10 balls. 1 green, they're all the same color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're looking in the side sometimes, okay? And each one of those 10, I can't do it because it's too small, but each one of those balls has a number on it, 1 through 10, okay? So now, what's the probability of picking ball number 1? So let's say if X equals 1, my probability of picking the ball that has a 1 on it is 1 over 10 because I have 10 balls. And I could say, what's the probability of picking a ball with 2 on it? Actually, let me write it like this. Probability of picking a ball with 1, probability of picking a ball that has a 2 on it is also 1/10. And all the way down to the probability of picking a ball with a 10 on it is also 1/10. They have an equal chance. They're all the same size. They may not look like that in my picture, but they are. Okay. So these are discrete values. I can't pick 1.1. I can only pick 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So a discrete random variable has a collection of values that is finite or countable. Well, 10 is finite and I can count them. If there are infinitely many values, the number of values is countable if it is possible to count them individually, such as the number of tosses of a coin before getting heads. So it always is separated. So for example, if I were to draw this graph, that's I guess where I was going. Here is let's call this P of X. And let's call this X, okay? So the probability of getting a 1 is 1/10. The probability of getting a 2 is also 1/10, and so on, right? Now, can I connect those dots? No, because there's no probability, or there's no possibility even of getting a 1.5. So I can't put a value in between 1 and 2. That's what makes this discrete. Okay, so discrete has distinct values. Okay, now let's talk about what is something that is continuous. So let's say I want to measure the heights of, or I want to know how many, what's the probability of a man being, okay, let's write it down like this. Let's do height. And we say, what's the probability of a man being 6 feet, 1 inch tall? Okay, well, we don't know, right? Because the chance that someone's exactly 6 feet, 1 inch tall is very, very small. Maybe they're 6 feet, 1 inch and 1/100th of an inch tall, right? That's a possibility. So when I graph this, okay, we'll call this height. And we can call this the probability of X, right? And in reality, this is going to look like my bell curve. Oh, let me draw a better bell curve. Okay, so now let's say the mean value of the height of a man is 5 feet, 10 inches tall. Okay, that's the mean. Mu, right? So 6.1 or more, maybe is out here, okay? And maybe we want to know the height of, so if we want to know the height of someone who's exactly 6 foot 1 inch tall, it's probably really small, right? Maybe even 0, because maybe everyone's got a little less or a little more than 6 foot 1. But a better way to say this may be, what's the probability of someone being between 6 feet tall to 6 foot 2, 6 foot 2 inches tall, right? That would include 6.1 as well. Now we actually have 2 values. So I could say, let's say this is 6 feet here, and we could say, let's say this is 6'2" here, and the probability of someone being between 6 feet and 6'2" is the area under this curve. So let's just say this is 6 feet, and this is 6 feet 2 inches. Okay, we would have between here and here, if we could find the area of that, we would know the probability. Okay, so let's see, let's read this. A continuous random variable has infinitely many values, and the collection of values is not countable. Because how would I know exactly how tall somebody is? Maybe they're 1,000. If I could really measure them down to the very, very, very small amount, like 1/1,000,000th of an inch, right? Well, then probably no one would be the same exact height. But we do have a range. And also we can write this. A better way to write this, actually, let me rewrite this. I'm still going to say between 6 foot and 6'2", but I would write it as the probability that 6 foot is less than or equal to X, which is less than or equal to 6 feet 2 inches. So that still is between 6 feet and 6'2" and includes both sides. It includes people who are exactly 6 feet tall and exactly 6 feet 2 inches tall. But I can't count all the values that are between 6 feet and 6'2". So I have to have a range, and I can say it's the area under the curve. Let's see. Possible to count the individual items because at least some of them are on a continuous scale, such as body temperature, height, right? You can't go from when you're growing, you don't go from 4 foot 1 inch to 4 foot 2 inches, right? You have to hit every single number in between, whatever those heights are. And there's infinitely many of those. So this is continuous, and I can draw a graph. Notice my graph is a continuous graph. It doesn't stop somewhere. Whereas these are just dots, this is a continuous line. Okay, hopefully that makes sense. So here's the requirements for a probability distribution. Every probability distribution must satisfy these 3 requirements. There is a numerical random variable X. So we don't want categories. We don't want to say grapes. We want to say we have to have a number. Okay. The sum, that this means the sum I don't remember if we've talked about that before, so let me just say it again. This is a sigma. And if I say I want to sum all my X values from, let's talk about the one from the one before. Well, so let's go to the one where I drew here's our box filled with 10 balls, right? So the probability, if I add up all these probabilities, 1/10 plus 1/10 plus 1/10, all 10 times, right? So for example, for that example, we would have the sum would be of X, of P of X actually, is equal to 1/10 plus 1/10 plus, this just means there's numbers in between, okay? And there's 10 of these, right? Because we're going to add each one, and there was 10 balls. We add all these up. 1 is the same as saying 10 times 1/10, which equals 1. So there we have number 2. The sum of all the probabilities has to equal 1 because X can assume any value. The sum of all probabilities must be 1, but sums such as 0.999 or 1.001 are acceptable because they can result from a rounding error, right? I can round 0.999 all the way up to 1, and I can round 1.001 to 1 also as well. So, but the sum has to equal 1. All probabilities are between 0 and 1 for every individual value of the random variable. So basically we're saying our probabilities are between 0 and 1. They're always going to be decimal numbers, right? And whenever I have a decimal number, let's say I have 0.37. Okay, that's my probability. To change that to a percentage, I have to multiply by 100. I multiply by 100. So if my probability is 0.37, I multiply by 100. It's the same as moving my decimal place 2 places to the right. Multiply 0.37 times 10, and you get 3.7. By another 10, which is 10 times 10, you get 37. So 0.37 as my probability is the same as 37%. Okay, so why do I have to be between 0 and 1? Because 0 is the same as 0%, which means I have no possibility. It's impossible for it to happen. So I can't have negative probabilities. What would that even mean? And 1 times 100 is 100%, which means that if I want to get that number, if that's the only, like if I have, let's say I have 1 coin and there's heads on both sides, what's the probability of getting a heads? 1. What's the percentage? 100%, right? Because both sides have heads. So basically everything between 0 and 1 is really the same thing as between 0 and 100%. All right, let's look at this example. So let's consider tossing 2 coins with the following random variable. X equals the number of heads when 2 coins are tossed. So let's make our sample space. We talked about our sample space before, so it could be heads, heads. It could be heads, tails. It could be tails, heads, or it could be tails, tails. And that's the only possibilities, right? So X here is the number of heads when 2 coins are tossed. Okay, so if I want 0 heads, there's only one of those, right? Tails, tails. So that is 1. So remember the probability of 0 heads is equal to the number of successes over the total. Or I think I've called it the part over the whole before, maybe not. So I only have 1 success. I have 4 total possibilities in my sample space. So 1 divided by 4 is 25%. Let's use blue. The probability of getting 1 head. So 1 head, 1 head. That's going to equal 2 out of 4, which is 1/2, which is equal to 0.5. This I guess I should put here 0.25. Okay. And lastly, let's get a new color. How about purple? So lastly, the probability of two heads equals, well, there's only one of those. So it's 1 out of 4, which is equal to 0.25. So that's how I get my values. This is my, now I've set up my table. Okay. Let's see. The random variable X in the table is a discrete random variable. It's very countable. I only have 3 possibilities. It's finite. So it really does satisfy all the requirements of being a finite value. Where's my mouse? There it is. I think this is, well, let's read it. With 2 coins tossed, the total number of heads can be 0, 1, or 2. And the table that we had before is a probability distribution because it gives the probability for each value of the random variable X, and it satisfies the 3 requirements listed earlier. Okay, so the 3 requirements were, it's numerical. Yes, the random variable X is numerical. It was 0, 1, or 2. When I sum up all the probabilities, it was 1. Well, I'll show you. And the probability of each event is between 0 and 1. So this is X. These are my values, and they are numeric. If I add up 0.25 plus 0.5 plus 0.25, I get 1, which is a requirement, right? That's number 2. And every single probability for each individual event is between 0 and 1. And that's true as well. Okay. So we're in good shape. And this is what I just said. Yes, exactly what I just said. Here's a histogram. Remember the histograms. This is a graph of the probability distribution of that table. Here, maybe I can copy and paste it so we can look at it. Copy. Paste. All right. So 0, that's my first line. My probability is 0.25. 1, my probability is 0.5. And 2, my probability is 0.25. So this is a histogram of what that table is. Remember, we said it was tables, formulas, and graphs. We have a graph and a table. Here's the formula. So a probability distribution can also be of the form, in the form of a formula. So here's a formula. So we can find, and I don't know if you've seen this factorial is the exclamation point. So if what factorial means is, if I say what is 10 factorial, that's equal to 10. Well, let me give you the general. Let me do the general first. So x factorial is equal to x times x minus 1 times x minus 2. I don't know how many x's I have, so we can only go to where we can go to. And it's going to go all the way down to times 2 times 1. So for example, if I said, let's not do 10, let's do 5 factorial. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. And that's really what factorial means. This exclamation point is called factorial. You are not going to probably ever do this, but let's just say. So I'm going to use the formula and show you how we got we can get the table. So I can say P of 0. Oh, very important. One more thing. Where should I put it? Put it here, comma, 0 factorial equals 1. So that's an important part. So if I want the probability of 0 heads, it's equal to 1 over 2 times 2 minus 0 times 0 factorial, which is equal to 1 over 2 times 2 factorial. 2 factorial is 2 times 1, right? Or 2 times 1 is 2. And then 0 factorial is 1. So this is 1/4, which is what we said it was before. The probability of 1 head would equal 1 over 2 times 2 minus 1 factorial times 1 factorial, which is equal to 1 over 2 times, and then 2 minus 1 is 1, right? 1 factorial times 1 factorial. This is equal to 1 over 2, because 1 factorial is 1 and 1 factorial is 1. So there's my 1/4, 1/2. And if I ask for the probability that we have 2 heads, we would have 1 over 2 times 2 minus 2 factorial times 2 factorial, which is equal to 1 over 2 times 0 factorial times 2 factorial. Oops. There's a factorial. Let's see if I can get that in there. Factorial. So that's equal to 1 over 2 times 0 factorial is 1, and 2 factorial is 2 times 1, which is really the same as 2, but I'll put it in there this time. So this is 1/4. So now we have probability of 0 heads is 1/4, 1 head is 1/2, 2 heads is 1/4, which is exactly the same as my numbers here, 0, 1, 2. So there's our 3 different ways we could find it, right? So let's stop here for a second, and now we're going to regroup, and we're going to talk about parameters of a probability distribution. Okay, so now, again, parameters of a probability distribution. So remember that with a probability distribution, we have a description of a population, not a sample. So the values of the mean, standard deviation, and variance are parameters, not statistics. The mean, variance, and standard deviation of a discrete, we know what discrete means now, probability distribution can be found with the following formulas. So basically the mean, we just take our x value and multiply by p of x. For the variance, which is the same as the standard deviation squared, we take our x value minus our mean. So whatever the difference is, we square it and then multiply that by the probability. And these are really the same. We're not going to do manual calculations, so nothing to worry about. And once we find our variance, our standard deviation is just going to be the square root of that. So no big deal. let's do an example. So here I have, this table is going to describe the probability distribution for the number of heads when two coins are tossed. So this is the mean. This right here is going to be the variance, right? When I sum them. Okay, so let's do these first. So x, which is 0 times 0.25 is 0. 1 times 0.5 is equal to 0.5. And 2 times 0.25. Let's do like this. It's too many dots, right? Times. And this is going to equal also 0.5. Now notice when I add these up, I'm going to get, because remember it's the sum of all of these values. And if I add 0.5 plus 0.5, I get 1. So now I know my mean is 1. Okay, now let's do the variance. We have here, let me move it over just in case. Okay, maybe not. So we have x is 0, mu is 1, we square it, and we multiply by p of x, which is 0.25. And this is going to equal 0.25. I'm just going to put it out here. Because we have 0 minus 1, which is 1, squared is negative 1, I'm sorry, squared is positive 1. 1 times 0.25 is 0.25. Here I have 1 with my x minus my mean squared times my p of x, which is 0.5, which equals 0. 1 minus 1 is 0. 0 times anything is 0. So this is 0. And then the last thing I have is 2, which is my x, minus my mean squared times p of x is 0.25. This equals 2 minus 1, which is 1. 1 times 1 is 1. Nothing to worry about there. And then I multiply that by 0.25. And again, I would get 0.25. The variance is the sum of all these numbers. Let me see if I can move this. I'm not sure why it's not moving. That's okay. So if I add these up, I get 0.50. That's my variance. So that's sigma squared. Okay. And I guess we should do the last one. So we got our mean, we got our variance, and our standard deviation. That's the only thing we didn't get. So my standard deviation there's an I in here, which is equal to sigma is equal to the square root of sigma squared, which is the variance. So we just say that sigma is equal to the square root. For this problem, let's do it like this. For this problem, sigma is equal to the square root of 0.5. And I'll get my calculator. That's equal to 0.707. And it just really depends on where you're going to round it to. Okay, so now I have also my standard deviation. And again, this is not how you'll be doing it, so nothing to worry about. So let's see what the interpretation of this is. When tossing two coins, the mean number of heads is one head. So if I toss two coins, it kind of makes sense. There's a 50-50 chance. So if I toss a coin, same as tossing one coin twice, the chance is that one time I'll get a heads and one time I'll get a tails, right? That's the average, the mean. The variance is 0.5 heads squared, because remember, it's squared. The variance was the value squared. So that's why I get heads squared. And the standard deviation, we got 0.707. And here we have 0.7. So they rounded it to 1 decimal. Also, the expected value for the number of heads when two coins are tossed is 1 head, which is the same value as the mean. We're going to learn about expected value in a little bit, not right now. But let me just say, the expected value is basically the same as the mean. If we were to collect data on a large number of trials with 2 coins tossed in each trial, we would expect to get a mean of 1 head. That's basically what this says. All right. I think, yeah. All right, so here, I think what we're going to do is go do a couple of problems, just so you can see how it works on a problem set that we have from my stat lab. Let's see. Here we go. So, number 1, 5 males with an X-linked genetic disorder have 1 child each. The random variable X, okay, is the number of children among the 5 who inherit the X-linked genetic disorder. So out of 5, either 1, 2, 3, 4, or all 5. Determine whether a probability distribution is given. Okay. If a probability distribution is given, find its mean and standard deviation. If a probability distribution is not given, identify the requirements that are not satisfied. So I'm going to click on my little bar here, and I'm going to open this in StatCrunch. And let's do that little thing I do. Where's my StatCrunch? Oh, that is StatCrunch, so I need this homework. So here's my values. And first thing I want to know is, does this, well, first, okay, we can look at a couple different things. Are all my X's numeric? Yes, they are. So number 1. Number 2, we're going to have to figure that out in a minute. Number 3, are all my probabilities between 0 and 1? And yes, we can see that all the probabilities are between 0 and 1. The one we need to really figure out is, do all these P of X's add up to 1? So I can go here to stat, summary stats column, and I want to know if all the probabilities, and we just go to sum and hit compute, and there it is. They do sum to 1. So yes, this table shows a probability distribution. That's basically all we have to do, okay? If it didn't have all the probabilities here between 0 and 1, then we would say no. If all the probabilities did not sum to 1, we would again say no. If the random variables, which are my X's, are not, the X's number values are not associated with probabilities, well, they are. And the random variable X is a category instead of numerical. No, they're numbers. All right. Now it says, find the mean of the random variable X, select the correct choice below, and if necessary, fill in the answer box to complete your choice. So we click close. We go to Stat, Calculators, Custom. And our values are in X. Our probabilities are in P of X. That's all I have. But that's all I really need, because now, look, it tells me that the mean here is 2.5. Did not mean to make a fraction. So 2.5, round to 1 decimal place, perfect. There we go. And last, find the standard deviation. We have the standard deviation. It's right there, round to 1 decimal place. So if I round this to 1 decimal place, I would have 1.1. Check. And there we have it. Okay, so I showed you how to calculate it, but you don't have to calculate it. Okay, and we're going to stop here right now because the next question, oh no, that's not true. The next question is part of what we're doing. So we got that one right. Let's go to question number 2. And let's open this and get our StatCrunch open. Okay, we're done with this. Let's read the question. Refer to the accompanying table, we have it over here on the left, which describes results from groups of 8 births from 8 different sets of parents. The random variable X, so basically that's right here, the random variable X is, they're saying the number of girls. So the random variable X represents the number of girls among 8 children. Find the mean and standard deviation for the number of girls in 8 births. So should we check to see if it's a probability distribution? I mean, won't hurt. So we go sum the columns, right? We look at P of X. We don't want them to trick us. So let's sum the columns. It equals 1. So we know we have a probability distribution. And then we have to find the mean. So we go to Stat, Calculators, Custom, all the way at the bottom. My values are number of girls. That's my X. The probabilities are my weights. I hit compute. And the mean is, it's right here, round to 1 decimal. It's just 4. We can put 4 or 4.0. Either one should make it happen. Yes. And the standard deviation, round to 1 decimal, is 1.4. And check answer. And that's it. I'm not going to go to number 3 yet because I know number 3 is something that we're going to talk about in a minute.